In this video, we discuss the pulse modulation in detail. Pulse modulation is to map the digital bits 0 and 1 into pulses, into waveform. And this waveform will be modulated into high frequency and pass through to the antenna. So the name is called pulse modulation. Although there's the terminology modulation here shouldn't be confused. For analog communications, we have this source message, EMT. We do not need to perform all this module. We do not need analog to discrete time conversion. We do not need to do quantization. We do not need to do pulse modulation. So we directly can modulate this analog signal directly to the high frequency band and pass to the antenna. So this is analog communication here. And this modulation module normally is analyzed in frequency domain because it's much convenient to look at the frequency change from the baseband. This is a baseband signal to the passband. So this is a passband after the modulation. And here for digital communication, here when we talk about a pulse modulation, we do not talk about frequency. We talk about a waveform. Because we only have digital 1 or digital 0, so therefore the pulse modulation is also called binary pulse modulation. So shorthanded BPM, so binary pulse modulation. And binary pulse modulation can be achieved by amplitude modulation or by position modulation. This is a two typical methods to achieve binary pulse modulation. Now let's look at the binary pulse amplitude modulation. It's a BPAM, which has this format. S small s EMT and M equals to 1 or 2. A has equals to AM G of T. G of T is one waveform, and AM is equals to A, that's greater than 0, some value. If AM equals to 1, that's yes, 1T. That's the waveform to represent digital bits 1. And if AM equals to 2, that's yes, 2. That's another waveform. Will represent digital bit 0. The amplitude is minus A, so this is negative. Let's look at this chart. So this is a waveform, GT of T. So this is GT of T. It's rectangular. It has a duration of TB. The magnitude is 1. We plot, yes, 1T is here because it's multiplied by A. The magnitude here is 1 GT of T. So we multiply by A, that's for digital bits. That's for digital bit 1. So the magnitude is A. Now for digital bit 0, the waveform is S2. The magnitude is minus A multiplied by this G of T. Minus A multiplied by this G of T, that's minus A. The rectangular change to the negative portion there. So in this case, digital bits digital bits 1 or digital bit 0 are represented by the magnitude change. And this waveform is defined, is there. This is a waveform. The only variable is the magnitude. This magnitude. So magnitude is changing in terms of the digital bits, either 1 or 0. So therefore the name amplitude modulation. But because it's a pulse modulation, that's a pulse amplitude modulation. Also because we only have 0 and 1, that's a binary. So therefore this is a binary pulse amplitude modulation. That's a BPAM. And T of B, that's a bit interval. What's the duration of this pulse? That's TB. It takes this time long to transmit 1 bit. So what's the bit rate? The bit rate RB equals to 1 over TB. So this is a data rate. This is a data rate happened in the digital communications. It is controlled by the width, the time duration of the pulses. If this pulses is very narrow, we have higher data rate. We have higher bit rate. Next, let's look at the signal energy in each waveform. So this is the energy E m equals to 1 or 2. So we do integral from minus infinity to infinity, the signal squared. But for both m1 and m2, the signal only has values from 0 to TB. So therefore, the integral interval becomes from 0 to TB. And then this is the waveform squared. Plug in this signal in this signal. The signal SMT equals AM GT of T, and AM is equals to A or minus A depending on the digital bits 1 or digital bit 0. And then we square that. When we square that, minus A or plus A squared, that's become A squared. For either AM equals to 1 or 2. So because this quantity is squared, so that's A squared. GT of T squared. So mainly you take this waveform, you do square. And then this square goes to the shoulder. That's the notation. And GT of T, it has a value of 1 from 0 to TB. So you do 1 squared, still 1. So therefore, the integral equals A squared TB. So this is the energy for each waveform, S1T and S2T. In communication system, there's terminology called energy per bit. In this case, because we only transmit either 1 or 0, so there's only 1 bit information being transmitted. Therefore, the energy per bit in this case equals to EM. That's this quantity. Sometimes one waveform represents several bits. For example, one waveform can represent 3 bits of information. So in that case, the energy in that waveform needs to be divided by 3 to obtain the energy per bit. Next, let's look at an example that if we have A equals to 3, the magnitude equals to 3, and TB equals to 0.5 second. So what's the energy, the signal energy in the waveform? The signal energy for each waveform that equals to A squared multiplied by TB, 3 squared multiplied by half, that equals 4.5. The energy is joule. And this is also equals to energy per bit because only 1 bit information is transmitted here.